So this is the second lecture on hybrid workflows. So we started learning about this on Wednesday. And from Wednesday's lecture, I didn't quite finish talking about auto differentiation. So I want to carry on explaining Autodiff and finishing that section before I move on. So I've got some recap here. So what I tried to show you on Wednesday or explain is that the vast majority of our scientific programs that we write, they can be very complicated programs, but they can be simply thought of as just vector functions, where the program takes in, many arguments usually, but these arguments are often just vectors and matrices and scalars and other such things. And their outputs are similarly probably some sort of scalar or vector or tensor or something like this. And so mathematically, we can just write this whole scientific program down as just a composition of vector functions. So we take some vector x as input, apply lots of functions sequentially, and then we get our vector y as output. And we call these intermediate functions primitive functions. So we can, even though we have lots of kind of complicated matrix solves and other things in this example, hybrid Navier-Stokes solver that we were looking at, we can pull those down to their very primitive operations. So they usually things like multiplications, divisions, trigonometric transforms, etc. So n here is usually a very, very large number. And so what I told you on Wednesday is that auto differentiation is a super powerful tool that has been developed through our deep learning libraries that allows us to efficiently compute these two quantities. So in particular, the vector Jacobian product, which is exactly this quantity here, and then the Jacobian vector product. And what I really try to tell you is that whilst we developed Autodiff primarily for training neural networks, what's amazing about it and what makes it so powerful in scientific machine learning is we can also use Autodiff to differentiate through these complicated scientific programs to start learning components in these programs. Okay. So yeah, just as an example, this is a pseudocode for learning a hybrid Navier-Stokes solver. So this is a traditional numerical solver for solving for carrying out fluid simulation. But inside the solver, we have a neural network here that's applying some learned correction. And to train that neural network, we just use autograd to get the gradients of some loss function with respect to the parameters of the network. And we just treat the parameters of the network as like additional inputs to this scientific program. So what is this torch autograd.grad doing behind the scenes? Well, what it's doing is computing this vector Jacobian product. So in this case, dl by d theta here is not a full Jacobian matrix because L is just a scalar. It's a scalar value. So the vector Jacobian product of this quantity is just a single number times by that single vector there. Okay. So then I talked about how we compute these vector Jacobian products, how Autodiff actually works, the machinery behind it. And the way that we get this vector Jacobian product is just to decompose the Jacobian down to using the chain rule so that we can get the Jacobians of all of these intermediate primitive operations. And then the actual algorithm works like this. It's very simple. You just start with the vector and then you go from left to right here in so-called reverse mode differentiation. Applying many vector Jacobian products, and these now are vector Jacobian products of these primitive operations. So to write like an auto differentiation package or library, all you need to do is first define all of these primitive operations, the forward pass of these operations, and then we need to define how we can apply the vector Jacobian product to iteratively compute the chain rule as we go through and we backpropagate through the computation. The other kind of cool trick that I talked to you about was that we don't need to usually fully populate or explicitly compute these Jacobians. Usually these primitive operations are very simple and their Jacobians are sparse, and we can take that into account to design an efficient Autodiff solver. Okay, who's with me? Who understands that? Yeah, great. Good. So this is where I got to. I was describing how we actually do Autodiff in practice. So Autodiff frameworks like PyTorch, TensorFlow, and JAX, they work like this. When we're, for example, let's think about differentiating or backpropagating through a neural network layer here, or 2 layers. So the first thing you do is when you define this in PyTorch or TensorFlow, and you run this function forwards, what it does is it computes a directed graph of these operations. So you can think of this function as just a directed graph where all of these intermediate elements, have lines depending on which previous vectors or tensors computed them. And then, like I said, these packages for each of these primitive operations that we're applying, they define the efficient versions of the vector Jacobian and Jacobian vector product of those primitive operations. And then depending on whether you're doing computing the vector Jacobian products, so doing reverse mode autodiff, or if you're computing the Jacobian vector products when you're doing forward mode autodiff, you either way you do message passing through this graph to just iteratively compute this vector Jacobian product of the entire function. So this is how it would look for reverse mode. You'd start with some incoming vector here. And remember, we're going from left to right, so carrying it out in reverse. And so we just do some message passing. So then we multiply that vector with the dy by db and dy by w2. And then just keep going backwards through the graph until we finally end up with the gradient of the output with respect to the first weights, for example. This is forward mode, so exactly the same. We're just going a forward pass through the network instead. So we start with some incoming vector again, and then it should be very obvious what we do. When we do a computation, we just also do the vector Jacobian product of that computation as well. So we update this vector as we go through the forward pass of the computation, just like this. So I think it's very interesting to discuss this question about the memory requirements of Autodiff. So I've got a question here. So can anyone answer this? How does the required memory, so if you think about the arrays that we have to store in memory to do the forward pass and also the backprop pass, how does this memory scale with the depth of the forward computation for the reverse mode and for the forward mode? And how does that, is it different? Does anyone know? You can also reply in the chat if you have an idea. Okay, so let me show you these animations again. When we're computing backprop, when we're doing backprop, to be able to compute, for example, this quantity here, so dy by dh or dy by dw, we need to know what the value of y is before. That's part of the kind of Jacobian. Similarly, when we go backwards through the graph, we need to have stored the value of h and the value of b and w1 to be able to go backwards through the graph. So to do reverse mode autodiff, we need to have computed and stored all the intermediate computations of the graph before we start doing backprop. Does that make sense to everyone? Yeah. So how does the memory scale with depth in that case? Yeah. Yeah. So the amount of memory required, it depends on the depth of the forward computation. So it's linearly dependent. So now if I show you the graph for forward mode, can anyone tell me how the memory is different? So now we're going forwards. We start with a vector. We do the first kind of set of primitive operations. We update the vector Jacobian product, and then we go through. So how much memory do we need in this situation? Yeah, great. So we don't need to store these intermediate activations because we're already updating the product as we go along. So it's really interesting, not always appreciated, is that when we do backprop, we have to store our intermediate computations, and that scales linearly with depth. When we do forward mode, we get memory independent Autodiff. So it's very, very interesting difference and can be used quite effectively, especially when we have really long kind of computational functions. We can maybe sometimes forward mode is better than reverse mode, depending on the gradients that you want. Okay. So yeah, I mean, I've explained in detail now what Autodiff is. But, in practice, you don't have to worry about this stuff, right? So we can just hand this over to PyTorch or TensorFlow, and this is what these deep learning libraries are so amazing at, is just doing all this stuff behind the scenes. And what this all just equates to in PyTorch is just calling, for example, loss.backwards, and it updates the gradients for us. But if you actually look at the kind of documentation of PyTorch and read it for Torch autograd.grad, you can see it's doing exactly what we've been talking about. So it computes the vector Jacobian product here of the output with respect to the input. And this grad outputs here is just the vector that we're doing in that computation. So hopefully you should fully understand how this kind of function is working now. So yeah, I mean, there are also a couple of other misconceptions about what Autodiff is or is not, in fact. So you should appreciate this by now, that Autodiff is definitely not symbolic differentiation. It also isn't doing finite differences. We're getting exact gradients when we're running Autodiff. So it simply is a way of efficiently computing exact gradients. So make sure you're aware of the difference of these methods. Yeah. It's just the vector that you apply. So when you're doing this vector Jacobian product, it's this incoming message. So remember, so let me go all the way back to the first slide. So in general, we have some vector function, and then Autodiff gets the vector Jacobian product. So this could give you a vector as output, or in fact, it will give you a vector as output. But typically what we're doing is we want the gradient of the loss with respect to the theta. So this, you can think of this as a Jacobian, but it's just one row, because the loss is a scalar value, right? So what's the vector Jacobian product of a single row? It's just a scalar times by that row. And we always choose that scalar to be 1 when we call loss.backwards in PyTorch. So typically we don't even specify it, because it's just assumed that it's 1. But if you're trying to differentiate, if here the output is not a scalar, but it's actually a vector, then you need to define like an actual vector that you're going to compute the vector Jacobian product with. So yeah, usually we don't really see here, it's just 1 when we're doing a loss.backwards. Okay. Any other questions before we move on? Okay. So yeah, I was introducing hybrid approaches last lecture. So I said throughout the course so far, we've mostly concentrated on replacing our scientific workflows with a neural network, and that neural network has some interesting understanding of scientific understanding, either through the loss function or through the architecture. But now we're really focusing on these hybrid approaches where we're keeping our traditional algorithms, and instead we're putting learnable components very tightly into those algorithms. And I showed you last lecture how we can use Autodiff to train those learnable components end to end. And so why are we doing this? Why are hybrid approaches useful? Well, as I was talking about, deep neural networks certainly have their advantages, but they also have some big disadvantages. For example, they need a lot of training data, they're hard to optimize, etc. So this is the key kind of idea of these hybrid approaches, is why don't we directly incorporate a neural network or some learnable component into our algorithms, just to either accelerate the workflow or to kind of learn the parts of the algorithm that we don't understand, or maybe allow us to learn kind of incomplete physics that we haven't put into the program. I also showed you this hybrid Navier-Stokes solver. So we looked at simulating fluids, and we realized that traditional numerical algorithms have a problem with discretization error, or said differently, the accuracy of these simulations strongly depends on the number of mesh cells that you use. And so with a small number of mesh cells, we get a really inaccurate kind of simulation. So we looked into this hybrid approach here, where we took the low fidelity solver, but we added a learnable component to it to try and improve its accuracy. What that learnable component did is we just put a neural network into the inner loop of the hybrid solver. And the network took each low fidelity step and tried to learn a correction to make it look more like the corresponding high fidelity set. And so, yeah, this is the pseudocode for the hybrid solver, and it has the neural network in the middle of the code. And we're using AutoGrad to differentiate through this whole algorithm end to end with a loss function that just matches the final outputs of the hybrid solver with some ground truth high fidelity simulation. And so, yeah, this is the key idea of hybrid techniques. We also call this differentiable physics, using Autodiff to differentiate and learn physical algorithms. So hopefully that kind of key idea you fully understand and appreciate now. Okay. So how do we do this in practice? Or like, how would you generalize this to any kind of scientific program that you want to learn? It's super simple, and this is advice that I give many people that want to try hybrid approaches out for themselves. There's like literally 4 steps that you have to take. So step 1 is just to take your traditional scientific algorithm and rewrite it into an auto-differentiation framework. This is usually the hardest step. This can take a long time depending on your traditional code. So if you think about high performance code, a lot of it is written in Fortran or like other C++, for example. So this can take a lot of effort, but once you've done it, you get some big gains. So for example, PyTorch or JAX, we'll be talking about JAX. I've got an introduction in a lecture coming up. So then step 2 is to then open up this algorithm and allow it to be more flexible. And what I mean by that is putting learnable components somewhere in that algorithm. So for example, like learning a correction of a discretized numerical solver, or it could be even simpler. It could just be learning like a single scalar value, maybe a time stepping value or something like this. Step 3, just grab some training data of what you expect the outputs of that algorithm to be. This is where your real world data comes into practice. We need to learn these algorithms from some sort of data. And then step 4, just train your algorithm with Autodiff. Just compute a loss function of the outputs and just let Autodiff get your gradients for you. And then added bonus, all of these deep learning libraries are designed for doing parallel matrix operations, and they run much better on the GPU. And the bonus is that once you've rewritten your traditional workflow, it will also run on the GPU. And depending on the type of computation that it carries out, it may well be an order of magnitude faster than a CPU implementation, or even more sometimes. Okay. So yeah, hybrid approaches insert learnable components inside traditional algorithms, and Autodiff is really the key enabler for not only hybrid approaches, but all the other SciML methods that we've talked about. Okay, so I'm going to move on to now the second part of hybrid workflows. And in this part, it's composed of 2 things. So first, I'm going to do some live coding with you just to show you how easy it is to write a scientific program in PyTorch and then differentiate through it and learn something about the scientific process. And then I have one other example of a hybrid workflow, which is more complex, really showing you kind of the limits of what you can do with hybrid modeling. This workflow is for solving inverse problems. So instead of carrying out forward simulation, we're going to try and learn something about some underlying parameters of the system. So I don't know if I'll get to this in this lecture, but we'll carry on next lecture if we don't make it. So yeah, we're going to be able, hopefully by the end of this part, you should be able to experiment with hybrid approaches yourself in PyTorch by using the code and understand kind of advanced hybrid methods. Okay, so what I'm going to do is switch. So if I share my Chrome tab. So I just want to check people in the Zoom. Can you see my Chrome, my Jupyter notebook? Okay, good. And you can see it here. Okay, good. Okay, so what we're going to do is investigate this problem. So who has seen this problem before? It's called yeah, all right, pretty much everyone. Okay, so I guess it's been on the internet a lot. It's quite a good interactive demo to teach people with. So this is just a really interesting problem, which is to say, if a ball is going to travel from one point to another by rolling down a slope, what should be the shape of the slope such that the ball arrives at the fastest possible time to the second location? And it's not actually intuitively obvious, in my opinion, what line it should take, like a linear line or a very steep line or something in the middle. And so, kind of long story short, there's a special curve called the Bekistochrone even, which is this shape here that gets the ball there the fastest. So there's some really nice math that you can use to kind of prove this or to derive the shape of the curve. But what we're going to do here is we're going to say, okay, we haven't got the equation for that curve. We just want to try and learn it from just using a neural network to approximate that line. So yeah, here's the problem again. What's the shape of the curve which a ball starting from rest and accelerated by gravity will roll without friction from one point to another in the least amount of time? So what we're going to do is we're going to say, we don't know what this curve is. We're just going to call it y as a function of x, in this 2D setting. And we just let the initial location be the origin, and then the second location be x2 to y2. And so, yeah, our approach is going to be, we're going to try and learn what this function is just with a neural network. So we're going to say the neural network directly approximates this line that the ball travels on. So how do we train this network? How would you train, or how would you try to learn such a network? The answer's on the yeah, well. Yeah, exactly. Yeah, right. So we're gonna minimize the thing we want to minimize. So the final thing is the time of the simulation. But that's important, right? So we're not going to minimize. We're not going to give the network examples of the line. We're going to minimize some other quantity that we actually care about, which is some quantity that is computed from that line. So this is where the hybrid modeling comes from. Is what we're going to do is we're going to, like, given the line, we're going to compute the time it takes for the ball to roll along that line using a physics kind of solver, and then differentiate through that solver to kind of learn the network. So you can kind of see how this hybrid approach is being designed now. How do we compute this total travel time for an arbitrary line? Well, we just use, distance equals speed times time, but we need to do an integral because the line is not a linear line. I'm not going to go through this in detail, but one way to derive this travel time in terms of f of x is just to use conservation of energy and plug that in and rearrange this integral. And what you end up with is the travel time is this integral, which depends on the gradient of the line here, and also the line itself, and also the gravitational constant. So what we need to do is we need to be able to evaluate this integral in PyTorch, given the output of the network, to be able to compute the travel time, and then differentiate through this whole thing to be able to learn the weights of the network. Any questions on the kind of overall approach before I talk about the code? Does it make sense that what loss function we're using? Yeah. And it makes sense that the loss function is some sort of integral over the gradient and the values of the network. Okay. So a couple of interesting things about the loss. One is that we don't just need the value of the line, we also need the gradient. So how are we going to compute that? Autodiff. Yeah, so we're going to use Autodiff twice, actually. We're going to use Autodiff to get the gradient of the line, but we're also going to use Autodiff to get the gradient of the loss function. So like we saw in physics-informed neural networks, we can use Autodiff in a compositional way. We can apply it many times, which is super powerful. So yeah, the exact solution, if you're interested, you can follow this link afterwards. It's a cycloid, it's a parametric solution. And we're going to compare to that when we plot the results. So, okay, so first we're just going to import torch, and we're going to just define a cycloid so we can compare that to the exact solution. And then the first thing I want to do is define this kind of flexible function that represents the line the ball's going to travel along. So we're going to use a neural network. Remember, I'm going to say here, the line is just approximated directly by the network. So the network should take as an input the x coordinate and give me the value of y as the output, right? That's just the line that it's giving. So what I have is just a simple fully connected network where it has one input, the x value, and one output, the y value, with a bunch of layers. And so now in my forward call, it's just going to, given the x value, it's going to return y. What I've also done here is give the forward call the value of x2 and y2. So this is the final point that the network, the ball is going to end up at. This is just to normalize my inputs. Remember, we have to make sure we have nice normalized inputs for our neural network. So that's just going to help me normalize x. Now I'm going to do something a little more clever than just say y equals the neural network of x. I'm actually going to use I'm going to use a residual model. So like we were talking about in hybrid methods, we can, if we know, like if we have an assumption about what the line should look like, we don't have to learn the whole thing. We can just learn the residual part of the line. So a good starting guess, for example, if I don't know what this line is, I could just say, okay, let's just start with a linear line, right? And we'll just have the network learn a correction to that linear line. Maybe that's an easier learning problem than learning the whole line. So we phrase our ansatz kind of the line is this. We're going to say, we're going to assume that the line is linear, and then we're going to have the network just learn some residual correction in an additive way. So it's actually very simple. So first we just compute what our linear line would be as a function, here. And the linear line is just, given the ball starts at the origin, is just, the gradient times by x, y equals mx plus c. So that's the linear part here. And so then we need to compute the residual part that the network's going to learn. So the correction to the linear line. So then we just pass x through our neural network. So this is self dot. So let's go through each layer. So the starting layer here, and then the hidden state, and then the final state, like this. So these are just the layers of the neural network that I'm passing it through. I've made a mistake there. And then at the end, we're just going to add the linear model to the y value like this. So you can see how we're applying this kind of correction. So I'm just going to change this, doing a few other kind of tricks to make sure that it converges quickly. The first is I'm going to make sure that the input to the network is normalized. So at the moment, x is going to range from 0 to x2, as I've defined the problem. What range should we normally have our inputs to the neural network? Yeah, 0 to 1, or so I'm using a tan h here. So what range do you think I should use so that I don't saturate the tan h function? Anyone else? Yeah, -1 to -1. Yeah. So what I can do is just normalize it like this, and now you can see when x is from 0 to x2, then I've normalized it to -1 to 1. Or I think that's right, or is that half that? It's fine as long as it's the right order of magnitude. And then the final thing I'm going to do is this. So I'm going to times the final output by torch.tanh x and torch.tanh x minus x2. Can anyone guess what that does? Why is that a useful thing to do? Why does that make any sense? So I'm taking the residual prediction of the network and I'm timesing it by tanh x and tanh x minus 2. Why have I done that? Okay, so what this is doing is it's asserting our conditions of our problem, right? So we know that the ball has to pass through 0, 0, and it has to end at y2, x2. And we designed our linear line. Remember, we're saying the line is the linear line plus the neural network correction. We already designed the linear line so that it already goes through 0 and x2, y2, just by using this equation for the linear line. So what value does the network need to add at the starting point and the end point? 0, yeah. So what does this do at x2 and x equals 0? Yeah. Well, more precisely, it just says whatever the output of the network is, x equals 2, this thing's going to be 0, and x equals 0, this is going to be 0. So it's just going to force this residual correction is to be 0. Yeah. Sorry. Yeah. Good spot. X2. So let me just check this. I think it's all good otherwise. X minus x2. Yeah, I think it's what I've written up here. So I think we're good. Okay, so we create that, and now all we have to do is train the network. So what I've got set up here is a simple PyTorch training loop, just like you've seen before. So creating the model here. We've got 8 hidden states and 2 layers. So it's a very small neural network. We're creating an Adam optimizer to train the network. So this is all standard stuff. So all we need to do now is to compute the travel time, because remember, we're going to minimize the travel time with respect to the network's weights to try and learn this curve. So we have to come up with a way to compute this integral. So how do we evaluate an integral? Or how would we do this numerically? Anyone have any ideas? Yeah. Quadrature? Yeah. Yeah. So we need to discretize this so we can compute it. So we can use quadrature. What I'm going to use is the trapezium rule, so like a even simpler method for now. But yeah, for sure, you could use something better. So what I've got here is we're going to sample x along the whole range. So we can compute that integral. We need to sample. We need to have many values of x. So we're just going to do a linear sampling of x, and then we're going to compute the model's output. So this is the prediction of the full line. And so what we need to do here is compute the travel time. So the first thing I need is dy by dx, which is this torch dot autograd dot grad. So y and x, and then we need the vector of the Jacobian product. So we're just going to do 1s like x. And I have to get the 0th output of that output there. So this is where we're using autograd to get the dy by dx in the time value in the integral. So once we've got this, then we just need to compute the function that we're integrating. So I'm just going to write this square root. So we're going to say f equals torch dot square root. And then I think it's 1 plus dy by dx squared by 2 times g times y. Like this, 1 plus that squared, 2 gy. Okay. And then we're going to use the trapezium rule to integrate, or basically sum the values of x together. Yeah.
this case, would it theoretically be possible with a slightly bit of a simpler to calculate it analytically and we have the gradients in the networks?
Yeah. It may well be, yeah. If you can write that analytically, then yeah, sure, it's much better. But otherwise, quadrature or Monte Carlo sampling or something, there's other ways to evaluate it. Okay, so we're going to use the trapezium rule. So Torch has this function called torch.trapezoid, so it makes it super easy. So it just computes the trapezium rule. So it's going to approximate that integral with these points. So I just need to do t. So this is the total travel time. Is torch.trapezoid, and we need to give it the function values and then the x values like this, and then we say we're going to sum across the 0th dimension. So I think this is pretty much it. The rest is just to call torch t dot backwards. This is doing back prop to get the gradients of the network. And we take an optimizer step and we do that in a for loop, and then we're just going to plot the curves as it learns. There is one thing that I've missed, which is we need to create a graph here so that we can differentiate through that gradient graph as well. So let's see if it runs. I think it's going okay. Yeah, okay. So what I've got here is 2 plots. So one is the prediction of the full line. So this is the linear model plus the neural network correction. And so this is very interesting. So this is before we've done any training steps. So what you can see already is it looks like a linear model. So this is why we had this linear model as a starting guess. It's got a little bump here, so maybe the network's done a little correction from its random initialization. Also, it passes through those 2 points. So we've done these hard boundary constraints, which is really nice. So whatever the network learns, it's always going to pass through the 2 points. Then the orange curve is the brachistochrone. So this is the cycloid solution. And then you can also plot the velocity of the ball as it's traveling. It's just interesting to look at it. So yeah, as we're optimizing the network, we're reducing the travel time that it takes. This is the thing that we're optimizing, and we just start to converge closer and closer onto this exact solution. So that's it. That's an example of using a neural network inside of a physics workflow, a workflow to compute travel times and differentiating through the whole workflow to learn that component of the program. Yeah. Yeah, I think that would be that's something we should test. I think it probably depends on the Lagrangian, but what might be interesting is if you wrote a general purpose code that could take any Lagrangian as input. There's an aside, there's these things called Hamiltonian neural networks, which try to learn Hamiltonians. This is a whole different subject, but people are trying to learn at this sort of higher level of abstraction as well. And that gets really interesting, those types of techniques. Yeah. Any other questions? Okay. So we've got 5 minutes left. So I'm gonna start the next section, but we'll finish it on Wednesday next week. So what I'm going to do is describe one final hybrid approach, probably the most advanced hybrid approach that I'm going to tell you about. And we're going to design an algorithm, a hybrid algorithm, to solve this problem. So this is computed tomography. Hands up who's seen this before or knows of this kind of general problem. Okay, so this is an inverse problem, and the goal is, well, computed tomography is used for medical diagnosis. Like is used, probably everyone's had an X-ray scan in their lives at some point. And what we see when they give us a scan is these images, but that's not actually what the instrument is recording when you have the X-ray scan. What the instrument actually records are these things called sinograms, which are these really interesting, like wavy kind of images that they record. And so what is actually happening in an X-ray or a computed tomography scan what you have is some media. So for example, someone's head or some other part of your body, and you have an X-ray source, which you can think of just as a point source. And these X-rays just travel through straight lines of this media and end up being detected at some screen here. And what we actually detect is the intensity of the X-ray at the screen. So after it's propagated through the whole media. And so what this sinogram is showing is just the intensity along this axis here. And the other thing that we do in the experiment was we rotate the media around and we record, the intensity as a function of rotation. So that's the other dimension of this image here, is the angle of rotation. So this is a little graphic showing, if you recorded the intensity through this media, this is what you would get. So the intensity that we record is varies, and it just depends on the absorption of the media itself. So you can think of each part of the brain here as absorbing the X-rays differently. And this is what we eventually want to end up with, is this image of the absorption. So this absorption is a function of X and Y. We can write this mathematically using our understanding of the physics. We know that actually the intensity is just a simple integration, a line integration over the line the X-rays traveled and the absorption function itself, or the absorption image. So does this make sense, kind of the problem and the data that we have and how we want to solve it? We want to go from this observed data to our actual underlying image. Okay, good. And so here's the inverse problem. I've just described the forward problem, which is just integrating the image across all these lines and angles. But the inverse problem is, like, given some observed sinogram, can we get back to the image? And that's not always easy. In fact, it's very hard quite a lot of the time. And so, yeah, I talked about this kind of super high level kind of framework in the first lecture, where I said, many problems can be boiled down to this, where we have some physical system which has some input conditions. We have some forward model of that system, and then we get some resulting properties B. So the inverse problem is given B to decide what A is, or figure out what A is. And so I'm going to tell you how we do this traditionally, and then we'll talk about the hybrid approach next lecture. So traditionally, we often frame these inverse problems in general as an optimization problem. Fundamentally, it's a search problem. Given B, we want to find the possible value of A that produce B. So we can write it as an optimization problem. It's just a minimization of B, or a minimization where we try to, guess what A is, carry out some forward simulation of the system, and try and match it to the observational data. So this is an objective function or a loss function, and we can learn A just like we train neural networks by using gradient descent. So we can get the gradient of this loss function with respect to A, and then do a gradient descent step to learn A. So what this requires is that our forward model, so say if I give you an image and you have an algorithm that produces the sinogram, carry out this forward simulation of the X-ray, that needs to be differentiable, so that we can differentiate through F to get gradients of the loss function with respect to A. So we're going to be using Autodiff to differentiate through our forward solver, just like we've done, just like I've been describing before. You follow? Who's with me so far? Okay, good. So let me just draw it out as like a diagram. So this is the same thing, gradient descent, just drawn as a diagram. So we have to start with some initial guess of what the image is. Then we carry out forward modeling using a simple forward simulation. And then we have some real data here that we observe from our experiment. After I've had my X-ray, this is the data we actually receive. Then we create our loss function. We match our predicted image to the real data. Then we get the gradients of the loss function with respect to the image, and then we update the image. We do that many hundreds, maybe thousands of times, and we end up with some final model. So I think I'll stop there, and we'll talk about how we would improve this workflow and learn something about it in the next lecture. Okay. Yeah.
What's involved in the data?
Yeah, so maybe this label is a bit redundant. It's just F. It's just the output of the simulation. So yeah, it's you could just have this box here. Yep. Okay. Thank you, everyone. So see you on Wednesday next week. Okay, I think we'll get started. So we're going to carry on this lecture talking about this computed tomography example, which we started talking about at the end of last lecture. And what I'm going to explain to you is a kind of hybrid scientific machine learning workflow that's going to be able to help us solve this inverse problem. So let me just recap what the problem is of computed tomography. So this is just basically taking X-ray images of our bodies. So everyone's had a kind of X-ray scan before, I imagine. And what we see after we have the test is an image of whatever part of the body we've scanned. But what we actually record in the sensor is not the image. We record this so-called sinogram, which is the measurement of the intensity of the X-ray after it's gone through the media and once it's hit a screen. And we know from physics that this is just the integration of the intensity as a function of X and Y. So remember, each part of the media has a different absorption coefficient. So we just integrate that absorption coefficient in a line integral to get the intensity at the screen. And then what also happens in the experiment is the media rotates, or actually the X-ray source rotates around the media. And so that gives us this extra dimension in the image, which is the rotation angle. So it gives you this kind of these sinograms. And so the inverse problem here is to take our observations of the sinogram here and try and invert back for the image, or the absorption profile as a function of space. Everyone clear on the problem and the physics behind it? Great. Okay. So yeah, this is the inverse problem, to take this observed sinogram and go back to the image. And if you look at the kind of images that we actually produce, depending on the number of observations we have, so this is the number of detectors and the number of rotation angles that we choose, these images can be very noisy. So we can't. It's actually quite difficult to invert for the underlying image. Can anyone give me a reason why this image doesn't look exactly like the kind of perfect image? What would be a reason why we don't reconstruct a perfect image? Yeah, please. Yeah. 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 So you're right. If we just had one observation of the intensity, it's like a summation, and we're losing information of the absorption through that line. But what we do have is multiple observations. So actually, it turns out if you have enough kind of angles and enough detectors and enough lines that go through the media, then you can invert for the underlying image. And actually, the quality of the result depends on the number of kind of observations and the number of angles that we pass through the media. So we can frame this as an optimization problem, or more fundamentally, it's a search problem. We want to find the image that if we simulate the observed sinogram. So if we pass X-rays through that image and produce what we think is a sinogram, it should match what our real world observational data is once we've done the scan. So typically we'll frame it as an optimization problem where we have some loss function, which can, in the simplest case, just be the difference between the observed data and the simulation of the observed data. And then if this kind of forward model is differentiable, then we can just do gradient descent to update the image. And so I showed you this kind of picture. This is just a picture of what I just showed in the last slide. So what you do normally is you start with some guess of what the image is, usually some smooth or even constant guess. You take in your real world data here, you do forward modeling of the image to guess what the forward data looks like. This is what the synthetic data is here. And then we compute the loss function, and then we compute gradients of the loss with respect to the image, and we do a gradient descent loop. Who's with me so far? Okay. So as I was trying to point out, this is actually quite a difficult problem, depending on kind of the number of observations that we have, the number of lines here, and the number of angles that we scan over the media. And so this is fundamentally, and this is a general property of inverse problems. This is what makes it really hard to solve inverse problems, is that there's in general usually not enough information in our observed sinogram to be able to uniquely reconstruct the image. So another way of saying that is this is like a one-to-many map. There's many possible solutions that could produce this observational data. What makes this also hard is we often have noise in real-world settings, so there'll be noise from the detector, and this just increases the kind of ill-posedness of the inverse problem. So what we need to do to solve these in general, if we have a search task, we have to have some prior understanding of what the solution might be. So what does a typical image look like, for example? And we have to, the main way to solve inverse problems effectively is to try and incorporate that kind of prior understanding into our search algorithm to help us kind of find the right image. And so one way you can do this, there are many ways in inverse problems, but one way is to add an extra term into the loss function. And we call this a regularization term. So think back to our introduction to deep learning. We also regularized deep neural networks to find good networks that fit data. We're doing exactly the same concept here, but for inverse problems. So what this regularizer will say is it will take an image, your current guess of what the image is, and it will kind of give you a heuristic that says, yeah, this is a good image, or maybe this isn't a good image. So this regularizer might be higher for a poor image and low for a good image. So one that we use very traditionally is called total variation, and this just says that the gradient of the image should be close to 0. So what do you think that does? What types of images does that prefer? Anyone guess why we would use why we would prefer gradients to be 0 of the image? Yeah, please. Smooth, yeah, smooth. It's a smoothness constraint, yeah. So, I mean, this image is quite noisy. So if you think about the gradient, the spatial gradients of this image, there's going to be quite high or lots of spurious values. If I looked at the real image here, you can see it's actually smoother. So there are some step changes where the spatial gradients are high, but in the majority of the image, the spatial gradients are quite low. So this is kind of a good heuristic to add and try to guide our search towards a good image. Now, the other issue with inverse problems is F here. So when we compute this loss function, we need to take our image and do a simulation of what we think the observed sinogram is. And in general, this forward simulation can be very computationally expensive. So, if we're doing problems where we have to do like a finite difference simulation or finite element simulation, this can be just expensive to do one forward simulation. But then when we're doing gradient descent on this loss, we actually have to run the simulation forwards maybe 1,000 times, 10,000 times. And this makes the inverse problem really, really computational expensive to solve. Okay, so what I tried to give you there was just an understanding of the kind of challenges of this existing way to solve inverse problems, which is using gradient descent. So what I want you to do is have a quick discussion with your neighbor about ways that you might be able to improve this workflow by incorporating kind of a learnable element or maybe a neural network inside of this workflow somewhere. So remember, this is, we're talking about hybrid techniques. This is what we've been talking about for the last few lectures. And the goal would be to try and insert some learnable component or neural network, like in one of these boxes or somehow into this workflow, to either try and speed up the workflow or to try and improve kind of the accuracy of the final image. So just have a quick discussion with your neighbor, maybe just for a minute or so, and then I'll ask you what ideas you have. For people on Zoom, please feel free to write something in the chat and then I can mention it. Okay, so that was a quick discussion. Can anyone raise their hand and give me an idea where you might think about putting a neural network or some learnable component into this workflow? Yeah, please.
Definitely puts me down for forward modeling.
Yeah.
And just like, yeah, good quality input output data, which you kind of fit it to, and then kind of like quick forward model.
Yeah, yeah, great idea. So as I explained, this forward modeling here is very expensive to run if it's like if we have to run like finite difference simulation or something like this. So we can train like a surrogate model, just a neural network that approximates that forward model. Maybe it takes in the image and gives a guess of what the sinogram is, and that might be thousands of times faster. So yeah, good idea. Anyone else? There are many answers, by the way. Yeah, please.
Maybe the updating the model.
Yeah. Okay. Very interesting. Okay. So yeah. Yeah. I see. Yeah. So you would have a neural network in here somewhere that would take what would it take as its input?
Current model loss.
Yeah.
Yeah. Generates loss.
Yeah. 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 So maybe it learns like a better direction in this step. Yeah. Very good. Yep. Okay. Anyone else? There are many other options as well. Okay. So two very good ideas. You managed to guess exactly what I'm going to show. So well done. This is exactly what we're going to try and do. Is we're going to have a neural network here, which tries to take a better direction than gradient descent. So why is this a good idea? Well, we're just kind of trusting that if you imagine our loss landscape, in general, loss landscapes are very non-linear and non-convex, which means they have lots of local minima and they're very hard to navigate and also very high dimensional spaces to navigate. So just following the gradient direction is not by any means guaranteed to get us to the kind of global minima or even a local minima of the problem. So what we're going to try and do is we're going to try and search that space better by trying to learn a better step to take in that loss landscape than just to follow the gradient direction. Does that make sense, the general concept? I'm going to go into this in much more detail. But... Okay. So what is this network going to do? So it's going to take in, as you were suggesting, it's going to take in perhaps the gradient of the loss with respect to the weights. So, the step that gradient descent would take if we just did gradient descent. And then the image maybe, or maybe just everything else we have inside this for loop available to us. So we have the current image, we have the original observational data. We may even have some values of some regularization terms that might tell us how good that image is, like a guess of how good the image is. And so we just put this neural network into this inner loop of the hybrid solver. So I've got some pseudocode here. So what I'm writing in the pseudocode is just gradient descent. And I've written it out as a for loop as well. So again, this is just that diagram that I showed before. And this is the kind of standard gradient descent algorithm. So again, we start with an initial guess. We do this for loop where we compute gradients, then we take gradient descent steps. Nothing new. So what I'm going to write in the right-hand side here is the hybrid version where we're going to learn this gradient descent step. So this looks like this. And in the pseudocode, I've just highlighted here just the changes to the pseudocode. So you can see this is super simple changes. All we do is add one extra line inside of our gradient descent for loop, which once we've computed the gradients of our loss function with respect to the image, we just pass that through a neural network, which has some free parameters theta, which are just another additional input to the hybrid function. So yeah, the for loop looks like this. Same thing. All we do is just add this neural network correction to the gradient. Okay. Yeah.
You have like multiple neural networks in your workflow.
Yeah.
You then need to kind of pay attention to like training one first and then the
Yeah.
other. And this market way?
Yeah, good question. So what you're suggesting is maybe we could have a neural network that does the forward modeling and then does the gradient descent step like you were suggesting. So what do you think? Do you think, how would you train that?
I would maybe kind of fit one first on the data.
Yeah.
And then like add the other one and fit that on the data.
Yeah. It probably for learning forward modeling, that probably makes sense. You might want to train that model first, otherwise you're not even doing the forward simulation correctly. But in general, you have the option to train both at the same time. Because you can, well, so I'll show you how I'm going to talk about that. So now we need to think about how do we train this hybrid approach. So how do we actually train this neural network? So this is a question that we asked. Remember last lecture, or even the lecture before, we were talking about hybrid forward simulation. So this solver in the loop where we had a neural network. We had, for again, that hybrid algorithm had a for loop, and we had a neural network in that for loop. So how do we train this approach? How do we learn theta? If you just think back to how we did it previously, can anyone tell me? What loss function would we use? What inputs, outputs would we use? Okay, so I'll tell you, it's not immediately obvious. So what we should do is, or what we can do is think about the inputs and the outputs of this function. So remember, this is just a function at the end of the day that has some inputs and some outputs, and we just want to learn some of the inputs of the function. This is what I was trying to tell you with auto differentiation and differentiating through scientific programs. So let's just think about the kind of the inputs to that function and the outputs of that function. And that's going to help us define a loss function to train this neural network. So, I've just plotted the inputs of this function here. We just start with an image, a guess of what the image is, and our observational data. We run this complicated for loop with gradient descent and a neural network inside. But eventually, the final output of this function is just simply our guess at what the final image is, the solution of the inverse problem. So now that I've told you what the inputs and outputs are, can anyone think of a loss function that we might use now to train this? What are we going to match the output of the algorithm to? Yeah. Yes, exactly. Yeah, it's very simple. Our desired goal is to have this algorithm converge on the solution. So we should just match the output. We should have a loss function which matches the output of the hybrid solver to the ground truth image. So it's as simple as that. Like, we just say, here's our loss function. We just say, so H here is just the whole hybrid function, which takes in, our guess of the image, our observational data, and the parameters of the network. And we just match this whole output of this function to a set of ground truth images. So A here, we assume that we have some ground truth images or many examples of ground truth images that we can do this to. Does that make sense to everyone? So our training data is basically many thousands of examples of true images and some observational data based on those images and some starting guess, basically, which we can generate. And now you should realize that we can just differentiate through this whole thing to get the gradient of the loss with respect to the parameters. Because as I was saying, these scientific programs, we can just think of them as vector functions, and we can use Autodiff to just get gradients of the output of that vector function with respect to the weights of the neural network. So yeah, we're just doing a very simple outer training gradient descent loop here, where we're running gradient descent on gradient descent to train a network. So this is where it kind of gets a bit spicy or a bit exotic, because we're doing kind of learning to learn. We're like learning an optimizer to kind of learn the inverse problem. So this for loop here, you start with some initial guess of what theta is. You run it through the hybrid solver, you would compute your loss function, then you just use autograd to get the gradient of this loss function with respect to the weights of the neural network. So what we call this is like, yeah, we call it gradient descent on gradient descent, or like learning to learn, or this is also known as meta learning, depending on what field you want to talk about this. Any questions on this so far? Okay. And so this paper from Adler is a really good paper, and it basically proposes this technique where we try and learn the update step for CT imaging. And this is, long story short, this is the kind of example of their learned gradient descent with this learned update versus just the traditional version of gradient descent. And what you see is that the learned solver, once we've trained this neural network to update the gradients and step in a better direction, does seem to learn like a smoother and more accurate solution to the inverse problem. So we don't just have to stop there. We can actually carry on. And so what we just had a discussion on was, well, why not just add more learnable components to this workflow? We don't just have to learn the update step. Maybe we can learn other parts as well that we're not kind of sure of, or that we want to speed up. So yeah, we already kind of had this discussion. Another place that we could add it, for example, is in this forward modeling step. So this is the forward modeling here. In this case, it's just a numerical integration to get the line integral of the rays. But we could maybe replace that if that was expensive with an approximate neural network, for example. The example that I've got here is actually a different idea, and it's to learn kind of the lambda hyperparameter of the inverse objective function. So this, remember, our objective function in the inverse problem is to say what's the difference between our estimated observed data and our true observed data. And then we add this regularization term to try and guide the search towards like a reasonable image. And we have to choose some kind of weighting of these two different loss terms, and that's a hyperparameter that we would typically scan across just to kind of tune it to work the best. But we could try and learn this in the same way. You could just treat that as a learnable parameter. So this is two different ideas for learning this workflow. So this is kind of the key idea that I want you to take away from this kind of advanced example of a hybrid workflow is that we're not limited to just replacing one part of the workflow with a learnable component. We can put learnable components throughout the workflow, and we're kind of free to choose where we want to learn those parts. So it would probably be a bad idea to replace everything. Then you would just have a really ill-defined algorithm. This is where your kind of common sense as a scientist comes in. You have to really understand your traditional algorithm and know the reasonable places where you actually want to learn a component and whether that still makes a reasonable algorithm as output. So yeah, in summary, these are all the kind of ideas that I have of putting learnable components into this workflow. So you could put it at every single step. You could have, for example, a neural network here, which gives us a better starting model. So it turns out the starting model is crucial for these inverse problems to solve. If we don't start with a good approximation of the solution, they often don't converge at all. So we could have a neural network which takes the observational data and just produces an initial guess of what the model is. This could already solve the problem depending on how easy the inverse problem is. Then we could, as you suggested, have a forward model which we learn, which is much faster. We have this update step that we're learning to try and navigate the search space or the loss function better. We could learn a regularizer instead of just the lambda hyperparameter to add the regularizer. We could actually learn like a function that takes the image and tells you if it's a good image or not. Who's heard of discriminator networks or generative adversarial networks? Hands up. Yeah. So what's a discriminator network? Does anyone know? What's the input and output of a discriminator? So what a discrim, yeah, go on, you got it.
I think it gets even same images.
Yeah. Yeah, basically, yeah. So a discriminant in that when we apply it to image generation, it takes in an image and tries to tell you if that image is fake or if it's true. So we could use like a discriminant type network here, where we could have the network takes the image and tells us, is that a good solution to the inverse problem, or is it a fake image? Is it not a good solution? So people have done this as well, train like discriminator regularizers inside their algorithms. And then what's brilliant and about hybrid workflows is that we can just learn this so-called end-to-end, right? So we take the outputs of the entire algorithm and we match it to our desired output. So we optimize what we care about, which is the final image that's output by the algorithm. And this is where the power of AutoGrad comes in. AutoGrad just lets us get these gradients of the loss, differentiating through this whole kind of hybrid workflow to get our gradients. Any more questions on this? Otherwise, I'll move on. Yeah. Yeah.
Why is it even needed to look at hybrid approaches?
Yeah. Oh, okay. I think you've got the answer there. You just said it. Yeah. So good question. So the question was, if this network takes the observational data and tries to guess what the image is, why do we even need this algorithm? Well, the answer is, so people have done that as well, for sure, and it can work. It's just that if your inverse problem is very ill posed, so there's a one-to-many relationship between the observational data and the possible solutions, then this will pull out maybe just one of those solutions. Or more likely, if you use like a simple loss function, it will actually give you like the average solution, which is not actually desirable. If you might get a very smooth average kind of type of image. So there are ways around that, but yeah, this is what I'm trying to suggest here is that is a good first step, but then we can build on it and learn solver around that to improve it even further. Yeah. Yeah.
These problems are so hard. How do we get
yeah, so for CT imaging, yeah, there's no ground truth available, perhaps. But what we could do, and what we usually do, is just do a very high resolution image, an expensive, create an expensive training data set. So there are, for example, CT scanners in like research labs that are like super high resolution, that have many, many rays and many, many angles to give us a really high resolution image. So we can use that as ground truth to then solve a problem that has maybe less observational data. But yeah, I mean, it's a limitation for sure. Yeah. Yeah.
This about a huge model relational,
okay.
Distribution.
Yeah.
Of the images.
Yeah.
Is there also something that is done?
Yeah. Right. So I mean, a more mathematically like kind of rigorous way to frame inverse problems is to frame it in a Bayesian inference setting, where you're trying to invert for the posterior distribution. That's what you really want to do, because we know that it's like a one-to-many relationship. So there are for sure hybrid methods that you can insert into Bayesian inference, and maybe using a VAE or something like this to approximate some of those distributions is a way, but I don't have the time to go into it, but we can talk about it later if you, yeah. Yeah, for example, there's this kind of neat thing in gradient descent when you're training neural networks, is when the optimizer is bumping around the kind of local minima, you can think of that as sampling the posterior distribution. So you can kind of use that kind of concept to it sometimes. Yeah. Okay. Right, so what I'm doing here is just summarizing hybrid techniques before we move on to the next lecture, which is going to discuss something related, but not quite the same. So the key takeaway is that these traditional scientific algorithms, we can make them as learnable, like flexible, or as unlearnable as we like. And this comes down to our kind of, as a scientist, we have to make that decision of what parts of the workflow we think we can improve. And yeah, inside hybrid inverse algorithms, neural networks can be very effective at learning priors, so to help us converge on a solution when the problem is ill-posed, and also improving efficiency. It can replace the kind of the slow parts of the algorithm.